Right, hi guys, and welcome back to another video of GCP. Today, this is going to be the first video of Unit 3, and it's just going to be very light. It's going to be a quick introduction to vectors and matrices. The reason for this is that coming up, there are a few mentions of vectors, a few matrix operations, and they don't delve into it too deeply, but they do pop up again later. So I thought it'd be best to do a quick introduction to see what's going on, make you feel a bit more comfortable when you see this. But really, none of this is that important. It's just to get you familiar, and this will be very quick. So, vectors then. Right, so a vector is just a list of numbers, really. That's all I want you to think of when you think of or hear a vector. So, for example, here is V vector, V for vector in our case, and it's just a list. So it's got these big brackets. And it's covering 2 and 3, right? There are numbers in our list. And then we can just send that vector V, into a function. So we could just add 1 to it here. We could just do, V plus 1. And that would go through all the pointwise operations. So 3 plus 1 and 2 plus 1 for each of our items in our list would get added 1. Simple enough. And we get our resulting answer vector over here. Right, so it's a vector input and it's a vector output in this case. Cool. And then we can have some more, serious, some more big vectors going on. We'll definitely be seeing a few big ones. So this V down here, now it's the numbers 2, 3, all the way to 10. And we're going to do the same thing, V plus 1. And so unsurprisingly, we're just going to go 2 plus 1, 3 plus 1, all the way down to 10 plus 1, and the resulting vector is just going to be 3, 4, all the way down to 11 down here. Okay, so a vector is just a list of numbers, and we can use them to do operations too. That will be really handy moving forward. A matrix, on the other hand, is a bit more like a table. So it's got 2 dimensions. You've got your list or your column, and then you've also got many rows associated to that. Okay. So let's dive in. We need to walk through a little simple example here to get going. We would quite like to, let's just introduce these terms, right? We have some simple equation 1 here, where we have 1 banana and 1 apple is equal to some amount of value, right? And we would like to put this equation into a simpler form. Right, that's simpler for machines, for computers to handle. So that is vector notation, right? And in this case, we're trying to spot something in common here. We notice that we're taking something and multiplying it by something else, and then we're adding something multiplied by something else, right? And we're getting some outputs. And the output is the easy bit. That's that's Y for us. But if we could generalize something multiplied by something else and then adding something multiplied by something else, that'd be really handy. So that's where we have our vectors. So we get our banana and apple, and we stick them in one vector, and we get our coefficients, which are these numbers before our apple and banana, and we stick them in another vector, and that's how we represent it. So we'd get, this is what our vector equation would look like, okay? And that's, you'd read this off as 1 banana plus 1 apple equals 3. Okay, so that's our nice vector form. So let's go a bit more in depth. We needed another dimension. So now we need 1 or more than 1 equation to represent a matrix, really. So here we have now 2 equations. They're the same thing, really. We've got apples and bananas, and we've got some values. And we just want to represent it in a form of y equals mx, essentially. This output is something multiplied by something. So how do we do that? All we do is we define our vector x, in this case, to be the banana and apples, the thing that we're trying to solve for, which might be the features of the machine learning model. It might be things like the weightings or anyway. So they're the variables that we're solving for. And then we have also our matrix of coefficients. So this time it's a matrix. And all we're doing is we're taking 2 and 1, and we're sticking it in 2 and 1, and 3 and 5, and sticking it in 3 and 5. Okay. And then the same thing, now we have more than one output, right? We have five is associated to this, and 11 is associated to this. So we can just make y our a vector output. So essentially, this is how our answer would look. But you don't even need to know anything more than that. I think it's quite happy to leave it there and just know that matrices and vectors can be thought of as lists and tables of numbers that are used to save time and make more efficient use of computers for lots of these processes. So moving forward, if you see lots of loss functions which have A's and W's and B's, these can be all thought of as vectors and matrices. And we just do them to represent lots and lots of linear equations like these ones here, as that's really what we're doing over and over and over again. And importantly, all that we're doing is when we apply a function to one of our vectors or matrices, so such as this vector here, and we're applying a function plussing 1, we have an operation that will affect every single instance of the vector. So if we're just adding 1, it happens to 2 and it happens to 3, or it happens to every single one all the way down to 10 when we do it here, right? That's the important bit. So the vectors that we'll be seeing coming up with the weights and biases, there'll be tens of thousands, hundreds of thousands, maybe even bigger. So there are lots and lots of computations, and they're all stored in one vector called B for biases or W for weights. But essentially, that's it. So we'll leave it there, and yeah, see you in the next one for more content.